At the turn of the 20th century, physicists encountered a problem classical equations could not solve. The laws of physics that described the motion of planets and projectiles with absolute certainty failed when applied to the microscopic world. Classical models predicted impossible outcomes, such as a black body radiating infinite ultraviolet energy. They also suggested that atoms were inherently unstable, with electrons losing energy and spiraling directly into the nucleus in a fraction of a second. Resolving these contradictions required more than a single discovery. It required a two-phase reconstruction of physical laws. The first era, the old quantum theory, lasted from 1900 to 1924. Physicists kept classical mechanics, but added isolated quantum hypotheses to fit experimental data. Between 1924 and 1928, these makeshift patches were replaced by modern quantum mechanics, a unified mathematical framework built on probability. To understand the modern framework, we have to look at the specific failures of the first era that made a new mathematics necessary. In 1900, Max Planck introduced a mathematical intervention to solve the problem of black body radiation. He abandoned the idea of continuous energy emission, proposing instead that energy is exchanged in discrete packets, called quanta. He defined the energy of a quantum as E equals h nu, introducing h as a new fundamental constant of nature. While Planck viewed this as a mathematical convenience, Albert Einstein argued in 1905 that light itself is physically composed of localized packets, later named photons. Einstein used this hypothesis to explain the photoelectric effect, showing that the kinetic energy of ejected electrons is determined by the frequency of light, not its intensity. Despite these successes, the structure of the atom remained a crisis. Classically, an orbiting electron should radiate energy continuously and crash into the nucleus instantly. In 1913, Niels Bohr proposed a model that combined classical orbits with arbitrary quantum restrictions to prevent this collapse. Bohr postulated that electrons could only occupy specific stationary orbits where they do not radiate energy. He quantized the electron's angular momentum, restricting it to integral multiples of h-bar. This model explained the sharp spectral lines of hydrogen. When an electron jumps between these allowed orbits, it emits or absorbs light at a specific frequency, corresponding to the energy difference between the levels. While the old quantum theory could predict these results, it remained a contradictory hybrid, a system of classical mechanics held together by unjustified rules. In 1924, Louis de Broglie provided the catalyst for a more unified theory by extending wave-particle duality to matter. He proposed that every moving particle possesses an associated matter wave with a wavelength inversely proportional to its momentum. Werner Heisenberg followed this by abandoning the unobservable electron orbits of the Bohr model entirely. He developed matrix mechanics, a system based strictly on physical observables, like the frequencies of spectral lines. In this system, physical quantities are represented by mathematical matrices rather than simple numbers. This created a mathematical property called non-commutation. In this framework, the result of property A multiplied by property B is not equal to property B multiplied by property A. In 1926, Erwin Schrödinger approached the same problems from the perspective of continuous waves. He introduced the Schrödinger equation, which models the state of a system using a continuous wave function, denoted as psi. While the math was successful, its physical meaning was unclear until Max Born provided a probabilistic interpretation. Born showed that the absolute square of the wave function yields the probability density, the likelihood of finding a particle at a specific point in space. By 1926, physicists proved that Heisenberg's discrete matrices and Schrödinger's continuous waves were mathematically equivalent frameworks. Within 3 years, physics moved away from absolute orbits to a unified system built on probability. The non-commutative of Heisenberg's operators had a direct physical consequence, a limit on what can be known simultaneously. The 1927 uncertainty principle describes a trade-off. The more precisely the position of a particle is known, the less precisely its momentum can be determined. Mathematically, the uncertainty in position multiplied by the uncertainty in momentum must always equal or exceed h bar divided by 2. The equations show that uncertainty is a property of the universe itself, rather than a limitation of human measurement tools. This principle was solidified at the 1927 Solvay Conference. The physicists gathered here established the Copenhagen interpretation, which remains a cornerstone of the field. By the end of 1927, deterministic classical models were replaced by a framework built on inherent probability. One flaw remained in the 1927 framework. It was non-relativistic. It did not account for objects moving near the speed of light. In 1928, Paul Dirac generalized the theory to accommodate Einstein's special relativity. The Dirac equation naturally derived the existence of electron spin from pure mathematics. The mathematics of the equation also unexpectedly predicted a mirrored negative energy state, a radical idea which implied the existence of antimatter. The experimental discovery of the positron in 1932 confirmed Dirac's mathematical prediction. This progression from Planck's energy packets to the probabilistic systems of Heisenberg and Schrödinger led to the development of quantum field theory. In this framework, particles are treated as excited states of underlying probabilistic fields.